This award honors E.A.L. Smith, who developed the wave equation analysis concepts to a practical and useful tool for pile driving professionals. Additional development of the work added to the usefulness of the original approach. However, Smith's original development work remained at the center of the modern versions, giving evidence of Smith's genius. Smith, a mechanical engineer by education, was chief mechanical engineer for Raymond International, a company whose main product was the step-tapered, mandrel-driven pile. This is an economical type of deep foundation posed major challenges to the analyzing engineer. Working for a contractor made Smith aware of the need for an easily understood, rational, and realistic analysis. Smith's ingenious solution to the pile driving simulation problem enabled pile driving contractors to optimize pile driving equipment, reduce the frequency of excessive installation times due to unexpected hard driving, and pile failures due to excessive driving stresses. Smith stated, "I provided engineers with a tool that helped design driven piles not only for geotechnical or structural suitability, but also for drivability and therefore constructability." Considering the benefits derived from Smith's work, the awardee should be an individual who has demonstrated creative and original work that has helped the driven pile industry provide an economical, sustainable, and effective and environmentally conscious foundation solution. The creativity can be demonstrated in the form of innovative foundation design, manufacturing, installation, or construction procedures. It's my great pleasure to announce this year's winner and our first inaugural winner is Dr. Bengt Fellenius. Dr. Fellenius has deep geotechnical roots. His father was head of the geotechnical department of the Swedish State Railways and president of the Pile Commission for the Royal Swedish Society of Engineering Sciences. Bent's grandfather is the Fellenius of slip circle fame. His grandfather actually coined the term geotechnique and was the first person to use the term in a publication. With that baggage, it's no surprise that Bengt felt the need for leaving his native Sweden. Bengt was a professor of civil engineering at the University of Ottawa for 20 years, but most of his to-date 60 years engineering work has been spent in contracting and consulting engineering fields, dealing with a wide variety of assignments that encompass foundations, designed for industrial plants, water, sewage treatment facilities, bridges and highway projects, marine structures, and urban area development, as well as participation in special investigations, instrumented field tests, etc. In 1977, he was the third geotechnical consultant to acquire the pile driving analyzer for use in connection with pile driving projects. He is an internationally active foundation engineering consultant and author of more than 300 technical papers, mostly addressing pile driving and pile foundations. But his other topics of interest, such as soil improvement, foundation settlement, and in situ sounding. Dr. Fellenius has given lectures and courses to several universities and international conferences throughout North, South America, Europe, Southeast Asia. He currently lives in Sydney, British Columbia, Canada. Without further ado, I'd like to welcome Dr. Fellenius to the stage to discuss dynamic testing and analysis.
Okay. Thank you, David, for saving me time. It's a pleasure to be here. Indirectly, Ed Smith has, for me and for many of you, really had a great influence on your professional career. So it's a pleasure. A pleasure for me to present this lecture. This is the bearing graph. We've known this for more than a century now. That's the capacity, however defined, the driving effort, the blow count, blows per foot, inch or whatever, and we have a curve like this. This has been known from more than 100 years. And the main message here is the diminishing return. When you come here and you continue, it just flattens out. Whatever the increase of resistance is, we gain nothing. And that is about, depending on pile, soil, etc., about 8, 10 blows to the inch. You rarely gain anything with driving beyond 200 blows to the foot. That's been known. It's a staple information that we have. This was formalized in mathematical simple relation in a number of various formulas, putting mathematics into it. Well, we move forward another 3/4 of a century. We're into the early 70s. And we're at the site where we have standard penetration test here, 2 of them, with silty sand going into a clayey silt. And we're installing pipe piles, a group of piles, 23 piles, I think, to be taken down to a predetermined depth of 85 feet. I have a driving record for all. How do you like this? That is 200 blows per foot. This is the average penetration resistance as the pile goes down. Those are the maximum values every feet. That's the least. And this is actually the contractor, when he got down to here, and he had difficulty getting the piles down further, he increased the height of fall of the hammer to 10, 15 feet. And now he managed to get the pilots down to and the pile tip presumably to the estimated contracted tip. He got the pile heads down. Where the tip went, nobody knows. Pile toe went. This is another case where they do know where the pile toe went. It's here, at the front view. The pile went up there. The car was there before the piles. It happens. So we have a similar situation at the other case. And of course, it was subject to a lawsuit, and as fairness has it, the engineers, what was discovered that his survey crew, when they were to drill the site, it was flooded beyond the knees, so the boots didn't wreck, so so they drilled at the edge of the water. At the real site, there was bedrock at 40 feet. Well, that was in the mid-70s. Now we go back another 20 years from first to my own experience the first one was my own experience too, but on the side, so to speak. Here I am a graduate student at the university, undergraduate actually, and doing the first dynamic test ever on piles, 1959. And these are the curves. Now you're used to see them different. I will shift them. And you can see this is force, time to where you normally see it. And you have a drop hammers here and a light hammer there, heavy there. And you can actually see that at the light hammer, you have a narrow peak going up, and essentially nothing much happens after there. With a heavy hammer, you have a larger area underneath the curve there, and you actually can have a reflection when the wave is coming up from the toe. And for the first time, despite having a light hammer and about 4 or 5 times heavier hammer, the force is about the same. That can be, when you look at the wave equation analysis and so on today, we know this. That's what it comes out. But in '59, well, there was some understanding of dynamics and waves around, and the man in charge of this was Dr. Hans Christian Fischer at Uppsala University in Sweden. He probably knew. Nobody else did, and least of all the summer student. Amazing. You see the hammer, and you look at the result, and the force is about the same. But the action duration, therefore the length of the force, is longer. And that's the basic information on pile dynamics. Moreover, here's the diesel hammer, and we could see for the pre-compression before the ignition. That's the first time ever that's discovered. It's known that there got to be pre-compression, but in a 2 or 3 hundredths of a second, you can't see it until you have measurements, and these are the first measurements. Yeah. How the measurements were made, we had an oscilloscope, and you had a camera snap the picture. And then you traced that picture and got the wave traces. That's what they have summer students for. And then start putting the report together. Here, you see a shorter pile, that's the impact, and that is now the gauge down at the toe of the pile. Yeah, okay. It's hard for me and for you also perhaps to see that if we take and scale the time, the peak there is the peak down here. The peak there is the peak down here. And then when we go up in a mirror, we get the peak there. What happens there is what the toe experience is there. Again, fairly simple, obvious observations, but I remember the excitement seeing for the first time that we have a wave speed in a pile. These were small steps, initial steps, made by man, but the excitement was about as big for some of us as the later, about 10 years later, first step by up on the moon. And it is the beginning of the pile dynamics. But shortly after 59 came Ed Smith's first paper. It's a pioneering paper in the ASCE journal that started it all. From transferring a pile driving to some model of hammer, helmet, and a pile and soil into a wave equation model of element that can be handled by a computer. Ed Smith did not, as David said, work with the wave equation. He invented the wave equation analysis. The first one doing it. And you know what? The very first wave equation analysis was not done by computer, but it was done by Ed Smith on a Saturday, Sunday. He took every engineer, every accountant, everyone he could hold in the Raymond Company and put a series of tables along, that each one becoming a pile element. And then he, I suppose, was a hammer and said that the velocity and mass he has impacting that table, and they took it and did the calculation that he provided them with and passed it on to the next table, and they took it and passed it on to the next. And of course, there is a reflection, so they also, on the opposite side of the table, were the reflective people, and they sent up the wave, just like the computer does. And by the end of Saturday or end of Sunday, I don't know, he had one blow analyzed, proving to himself that it worked. Then came a couple of mainframe programs with the actual wave equation, very simplified, and we could do it. That's the wave equation at the bottom there. And of course, the academia latched on. And after Smith's paper, there were a number of papers discussing wave equations. And this is from one paper, and the author actually made this statement from the paper into an overhead graph, and that's a copy of it. What does it say? When you read through that, a little bit hard to follow. It's a long sentence. And Actually, it's very simple, very banal. It's not a profound statement at all about the difference between two analyses. But as you see, as often in academia, you present the most obvious things, and if it looks too simple, you can make it more sophisticated by using several terms for the same thing. It's an example of using 4 different terms for the pile tow. And of course, when you read it without the detailed knowledge, you're a little bit confused, and you translate that into the I don't understand it, so the statement must be profound. Often it is not. The original wave equation by Ed Smith was made into a mainframe program, and eventually with the latest development and the ultimate development is the GRL WEAP. Initially, it was in public domain, and I remember getting the first wave equation program back in around about 1976, and you got it in a box with punch cards. You have to take it to the important man in the company who was handling the mainframe inside a temperature-controlled room. He had a white coat, and you were very polite and gave it to him. Now, I bought it early. I wasn't amongst the first one getting it, but I got it early. But I have one record. I'm the only one who got it twice in the same week and paid for it both times. Because when I passed it on, the man took it and walked to the computer, and it tripped. And you just don't try to resort the cards. You buy a new shoebox. The key aspect here, you enter everything you need, but the key aspect is really the cushion of the hammer and the pile cushions. You can look at the, and of course it's modulus elasticity and COR, coefficient of restitution, which is essentially a different slope when you're loading up and loading down. Hysteresis, if you want. Now, this is a hammer cushion. It sits up here for those hammers who have a hammer cushion. Aluminum to lead off heat, and a softening material, in this case rubber. And the next one of importance is the pile cushion, usually wood, plywood is in this case. And when you compress and it's uncompressed back and forth, you generate heat. And you really compress. That's wood before it has been driven. That is when it has had a couple of hundred blows. Modulus of elasticity is a function of the strength and composition, hardness, if you want, of the wood and its thickness. There's quite a different modulus between the original and that. And which one do we put into the wave equation to predict the stresses in our pile? That's always a question. And of course, the other thing is what happens when in the real field. The heat is generated, and you can have this. The pile should have been stopped and a new cushion before this happened, because if you look at it, coefficient of restitution becomes meaningless. This is beyond restitution. Along with the WEAP came the pile driving analyzer, simply taking measurement of strain and acceleration and manipulate them in the pile driving analyzer. That's the pile driving analyzer of 1977. It's the third one that DRL or Pile Dynamics then sold, and I was the third consultant getting it, consulting engineer getting it. and starting to figure out what kind of an animal I had there and look at it and wonder if it would bite you or how you should treat it. You have a tape recorder to save the records, the analyzer, which has a paper tape to get the records, and you want to see the traces, you have an oscilloscope. You don't need to take photographs of it anymore, but it's there. And it's quite a hefty thing. You need 2 people to travel with it. And you have to give it its own seat in the airplane because it's too sensitive to be shipped. And what do we measure? And it is the force, of course, from the strain gauges. Now it so happens that we could measure the same thing with an accelerometer, because if you measure the acceleration and multiply with the impedance, material constant actually, you get force. The fantastic thing was that the people developing this, George Goebel and co-workers, used both measurements independent of each other to measure the same thing. You have force here, whether it's measured by accelerometer or strain gauge, the same value. So why double up? Well, it is the strange thing that if you have a reflection from the soil, force increases in proportion to the strength of that reflection. So force increases, but the pile slows down, so the physical velocity is less, so the 2 curves separate. And one of the great things of, that happened here with George Goebel and his co-workers is to recognize this, that the separation here is a graphic picture of the magnitude of resistance, capacity at one depth, if you want, and that this can be used. The other development is that to plot this and to see it better as in 2L of a C, that is the time it takes for the stress wave to go down to the toe of the pile and come up again. So that if this is now the length of the pile in a time domain, you can say that there is no shaft resistance until about halfway down, and then it increases, and then we have a toe reflection. And now we have something that can be analyzed. And at the beginning of the practical use of dynamics in foundation engineering. And the pioneers, you have George Goebel there in 1975. George passed away less than a year ago. And then you have the Frank Rauche, his early co-worker and still very active. And if you wonder, yes, that's the origin of the term pile monkey. Look at his feet. And with Frank was Garland Likens, and his here too. And other co-workers in this team developing what we now call the pile driving analyzer work. I'm going to show a couple of slides from very simple thing, but were revelations to me at the time, because I had never seen it before. I knew, for instance, about the setup and the increase of capacity with time. Here we have a wave from force and velocity. That's NED, we can leave that aside. And the force and velocity coming together here, we get some shaft resistance, and the separation, which is a sign of shaft resistance, a toe reflection here, which is negative, which is velocity. It means that there is no toe resistance. This is initial driving. 2 days or so later, we have a restrike, and look at the difference between these two areas. That's a setup. The first time I saw setup, well, of course I knew about it, but it gave me a chance of seeing the amount of setup and where is it. Bringing in the soil mechanics aspect into the analysis of the dynamics. And now another case was, well, I think it is in Utah, in early 80s. Driving a pile, and this is a penetration resistance, blow count as it's driven down. The contractor was contracted to drive the piles supplied by the owner. And of course, I had a bed per length, etc., driving to a predetermined depth. And then suddenly, from one day to the next, he couldn't pass. There's a kind of a cap here. So you have an artesian head here, that silty, clayey, hard layer that and loose silty sand or something up here. Suddenly, the pile stopped, couldn't be driven down. So he couldn't meet his contractual obligation to drive these piles down. And the owner said that, hey, your hammer isn't working anymore. You got to get a new hammer. And of course, that delay and tremendous cost to get it out there. And the contractor said, no, my hammer is working fine. It changed soil conditions. I will now have to drill through and then drive again. That will double the price or whatever. And what really happened? You look at all the things that have changed. The only thing really changed was that originally the owner had supplied half-inch wall pipes. But suddenly one day he ran out of those, or more convenient to put 3/4-inch pipes in there. And the 3/4-inch, no, not 3/4, I meant 0.375, the lighter pipes, they couldn't be driven through. What was the difference? The hammer that travels the same distance, the same weight, nothing has changed. Same 12 3/4-inch pipes. Well, we had the dynamic measurement. That is for the lighter wall pipe, and you see the results, force and velocity. And now we have the heavier pipe. The stress in the steel is about the same. But the stress times area, we have a larger force here. And force is the part that overcomes the soil resistance. So the heavier wall had a larger force. It could be driven through that layer and down. The lighter wall pipe couldn't. So of course, the contractor stopped asking about claiming changed conditions. The owner pulled off the thinner pipes and brought the heavier ones in, and the contractor and owner were great buddies and friends again, and the lawyers went home and cried. Now, this is the first one. The previous one is a case where we got to consider the soil, not just the dynamics, and the information go together. Here we start with the soil information. A cone penetrometer test with a loose soil here, a different soil there, another one there, very well described. And what I want to point out to you, this is pore pressure in the clay as we're pushing the cone down. In the sand, we don't really affect the pore pressure at all. That's conventional. That's what we normally see. At the same site, intermittently over a site, it was a large pile driving site for a city, actually. And now, this is the pore pressure. It dips, not become negative, but it almost disappears. That is, the soil is dilating when the cone is pushing. And when it dilates and pore pressure dips, it becomes denser, and therefore, the stresses doubles and trebles the cone stress. That means that we get also the pile is even more so displaying sand that dilates, and resistance goes up. It's a false resistance. We meet it at false refusal in some river estuaries and so on. But in this particular case, it was an extreme response. Here is the blow count with depth, driving the pile and stopping there. And suddenly, nothing is happening, nobody's working. It had worked itself up to the last inch was a resistance, so they stopped driving. And suddenly there's a sound, and the pile sinks 2 meters, 6, 7 feet in one thump like this. So put the hammer back on and draw on it, and the resistance goes up, and we're driving down. The cylinder part, so it was plumbed inside, and at that particular depth, about here, whether we drove down there or started there, the bottom of the pile was still at the same depth. What happened is the pile broke, and after the last blow, funnily enough, and the broken up pile and soil went up into inside of the cylinder, and the pile sank. And as we continued to drive, we're just crushing concrete down there. And now, that's a speculation, but we do have the measurements. This is the, I'll do this. This is the measurement at the last blow. You have a little bit of shaft resistance and a good toe resistance coming here. You can see the wave up curve there too. 3 blows later, we're now talking the first blow when we start driving again. This is the impact force, and no resistance, and just no toe response at all. And if you look at the wave up differences here, it's a significant difference. So the dynamic measurements confirmed the speculative opinion about what had happened. Solution to this problem was to use a cone and find out the zones that had this dilative response and drive down to it very carefully, and then take a while to drive through that layer or a couple of meters thickness and succeed the project. Combining, verifying this with occasional dynamic measurement. So you're putting the soil exploration and the dynamics together to reach the end of the project, the successful end of the project. Now, can't talk dynamic measurement without coming into CAPWAP. And that is the analysis of the test data. And just to remind those who are not familiar with it, we have 2 measurements, acceleration and strain. CAPWAP means taking one measurement and letting a calculation, the computer, running a wave equation analysis, here called CAPWAP analysis, to calculate, and the input is what the soil is and everything. The input from the hammer is the measurement. And the computer calculates the other measurement that is not touched, that's independent. You take the acceleration velocity measurement and you calculate, the computer wave equation analysis calculate what the other measurement should be. Now, when you do that, if the other measurements are calculated and the actual untouched measurements as in this case, force measured and force calculated, they fit right on top of another. Pat Hannigan, who did this, really went into the cosmetics here. It's a beautiful match, and of course the velocity match will be the same. Now we have then, with the CapWeb, back calculated the actual soil response, dynamic and static, and we're looking for the static that we can tell what the shaft resistance is and what the toe resistance is. That's what the CapWeb does. And the process is, again, Pat Hannigan work. You start out with a set, you don't get a match, you improve on it, you improve further. Now this is fine, you have to improve that, that's the cosmetic work, and you finally get a match. Some of this can now be done by a computer by itself, unaided. Of course, you need the judgment of an engineer around there. I've seen some terrible computer simulation believed to be the real. You always need to have a good, experienced fellow to improve on the robot. This was all new back in the 70s, and in the 80s. At that time, I was wondering. I had a fellow who was very capable in doing CapWebs. I never really got the hang of it. A decent one with the old ones, but I couldn't do it today. And I don't trust computers. I wouldn't like the computer to do it. But you have people around you that are very knowledgeable and capable on this. But back now in the mid-1980s, you say, how true is the CapWeb analysis to the results of a static loading test? So I took a couple of records, and I sent it out to every person in the world who was doing CapWeb analysis, all 18 of them. And 2 of them were Garland Likens and Frank Raucher, one or the other, I don't know which. And these are the capacities coming out of those CapWeb analyses. It's a remarkable coincidence between them all. But this fellow, he had never, this is association, it's a museum in Ottawa, in marine, soft, sensitive clay, very young clay. This fellow had never done a CapWeb or seen a pile driving in any other thing than sand. So he made some assumptions, got off. All others are very close. And there was a static loading test, which I didn't tell anybody about until afterwards. And the lowest capacity you possibly could derive from that test is here, and the highest one is there. And it's all pretty well inside there. It was very encouraging. Now you must remember that the 16 here, each one of them had either been trained by Garland or Frank. So whatever they do, the other ones will do too. Here's another one from Jones Island in Milwaukee, another case, and even closer together. No static test there on this particular pile. That was encouraging. I'd like to see if I could repeat it today. I'd be willing to do it, but we're talking about 1,000 people or more, I guess. I have no idea how many, but it's everywhere. And they're not all trained by Frank and Garland either. When we're happy and appreciating the agreement between all of these and look at details, you see that the toe resistance doesn't have the same narrow band here. When there is a matter of some compensating, not errors, but input assumptions here. If you're off here, it's corrected subconsciously up here, whatever. It is a very proven, very reliable method for finding out the key question: what is the response of a pile to a load? Along the road there was a discovery. Ed Smith assumed that the movement necessary for a pile to generate full resistance was 1/10 of an inch, and that's what was built into the first version of the cap wrap. Frank Rauche, on a project that I happened to work with, and had to have Frank come in and do a complicated cap wrap. We have force, velocity. There's quite a bit of a soft toe response, and that is at 3 meter, 11 meter, and 12 meter depth. And when we look at it at the more shallow depth, you can't make a match at the 1/10 of an inch, 2.5 millimeter. So, Frank realized that, never mind what Ed Smith said, quake is not always 2.5 millimeter, and he could make a match here at, I believe it's 20 millimeter. That much. And the same thing for the later on. They can't make a match with a 2.10 of an inch, but you make it with a different one, and it's not the same as the earlier. We have to recognize that the movement the pile has to, the distance the pile has to move is a function of the soil response, function of the grain structure and the number of items, particularly when you're dealing with the silty fine sand soils. It's one of the improvements and developments along the way till today. And it's important, because if we have a conventional pile driven at the low quake, we have a bearing graph like this. If at the large quake, it's bearing graph like that, and that's the capacity. It can have a significant difference, and you do not get the soils investigation that reports what the quake of the soil is. That comes with the local experience for the site. That's why in any foundation engineering, and particularly in pile foundation engineering, you need to have the local experience, past experience. I found that often it is the local engineer or the foreman in the field who knows more of what the pile will do than you can ever do with a dynamics analysis. But measurements, taking it properly analyzed, can lead you right. There's an awful lot of information. Ever since Ed Smith's first paper, there's been a lot of information on pile dynamics, and it's collected in this series of conference proceedings starting in 1980. And actually there is one that's not in here for 2012 and one coming up in June. And particularly the first volumes here have tremendous state-of-the-art reports on the concept. But if you ever get working in pile dynamics and get interested, get hold of them and read them. And a couple of additional things along the way. This is my bullseye representation. I used to call it about pile dynamics and cap wrap analysis. It's a perfect agreement between the cap wrap and the static. The static said this, the dynamic says that, and it's still a perfect agreement. If we consider what, and we should, what actually happens. This is a jetted pile. Now look at this. It's the same as in the static test. But here the toe has moved some 5 millimeter, I think, and it moved about 45 millimeter there. It's a matter of how much the pile moves. We can't get a cap wrap to say anything more than what the hammer put into the soil. If the pile moves, it moves because the hammer could put that resistance in. And what we're really analyzing is what the hammer put into the pile and soil. When the pile is not moving, we get, again, what the hammer put into the pile and the soil, but it's not enough to move the pile, so it's less than capacity. That's one way of expressing it. In this case, we have the toe resistance of the pile down here. In the static test, and in the dynamic cap-wrap on the restrike, it's here. Actually, it looks as if there is a difference there too, but we're forgetting one other thing, the sequence of testing. The dynamic came first and unloaded, and then came the static. So I moved this curve over, and it's a perfect agreement. It's a bullseye thing. I published it. I thought it was interesting, and it went into the I think, the fourth Stressway conference. And then, a couple of years later, I see a compilation by somebody who had plotted all the errors in cap-wrap and the difference between static test. And this was one of the more glaring disagreements between the static and dynamic. He got the data from the paper, but I think he didn't read it. That happens. Another case, speed up. This is prediction of capacity using standard penetration test and a large prediction. And then the engineers look at this and say, yeah, we need that as an ultimate, 2.5 times the working load. And we better play it safe and put it down there in case we have overestimated capacity. Now what happens? When the contractor gets the job, he knows that he's going to, in this case, drive to 1,600 kilonewton. He's not going to bring in the cost of a hammer and equipment to drive to 2,000 or 3,000 kilonewton. He knows what he's going to drive to. Now, turned out that he couldn't read that. These are actually cap-wrap analyses at initial driving. Even at the keep driving at 100 blows to the foot, he couldn't reach the minimum tip. Because the soil wasn't as weak as the engineers in that conservative approach thought. They erred on weak soil. The contractor meets the real. If he wants to err, he should err on strong soil, not on weak. So that's an incompatibility between the designers and the contractors in this case. At this site, here we stop a pile and then start driving again a couple of days later, and the blow count goes up. That's been set up. And then as we're driving, it drops, and now we're into denser soil. And it happens most of the time, and when we have, as in this case, a dynamic doing a cap-wrap, you can see that that is now the case, not cap-wrap, that's a case method estimate, a simpler method of getting a capacity, and you get it for every blow. You can see the resistance that this is driving against, and in restrike, you have this kind of resistance way above the working load and the presumed ultimate limit that you should have. They were driving the piles too deep. And of course, it was a costly remediation, litigation, and so on. And if looking at the data and bringing in the measurements, soil and dynamic, we can avoid these things. But we have to look at it. In this case, they didn't want to look at the dynamics. They had the standard penetration test. That's good enough, they said. Excellent test, but it's not good enough. And then along the way, we have a case where trying to sell them, instead of doing static tests, you should do a dynamic. And the dynamic was made along with the static. And the engineers looked at this and said, hey, this is our critical limit for the static. There's no correlation here. We're not going to do static. but with a simple recognition of plotting the dynamic in the sequence, you have a very good agreement. Actually, if anything suspect here is the agreement is too good. You have two different methods. They shouldn't be right on. But in this case, they probably are. You have a continued restrike and then a new static test. And it's really part of the same test all through. We'll skip these. It's interesting what dynamics and static in pipe piles, but I'm running out of time, so we have to remember a large number of other things. What can happen to a pile, and the beautiful art collection of Hal Hunt outside the Associated Pile and Fitting. Hal Hunt was selling pile shoes, and these are pipes he picked up that didn't have his shoes outside his office. So with this, thank you for your attention.